You've seen honeycomb your entire life, on honey jars, in nature documentaries, in geometry textbooks, and somewhere along the way, someone told you bees were impressive, talented, instinctively gifted architects. But nobody ever asked the real question. Why hexagons specifically? Not circles, which bees could naturally form by pressing rounded bodies together. Not squares, which stack cleanly. Hexagons, six-sided, geometrically precise, repeated across the entire structure without a single deviation. And here's the truth. Bees didn't choose hexagons through instinct alone. They discovered, through millions of years of evolutionary pressure, the single most mathematically efficient shape for storing maximum volume using minimum material. This isn't biology, this is engineering. If hidden systems like this change how you see the world, subscribe to Simple Facts. Before domesticated bees, before managed hives, wild bee colonies faced one absolute survival constraint. Wax is extraordinarily expensive to produce biologically. A bee must consume roughly 8 pounds of honey to produce a single pound of wax. 8 to 1. In a survival economy where every calorie represents flight miles, flower visits, and colony energy, wax is not a building material. It is a survival investment. Every cell built represents enormous biological cost. Wasting any of that wax, through inefficient geometry, through gaps, through structural redundancy, directly threatened colony survival through winter. The hive that wasted wax starved. The hive that maximized every milligram of wax stored more honey, fed more bees, and survived. Enter the mechanism. This is called the honeycomb conjecture, a mathematical problem that humans formally posed in ancient Greece and didn't rigorously prove until 1999. The question is precise. Of all possible shapes that tile a flat surface completely without gaps, which uses the least perimeter to enclose the most area per cell? The answer is the regular hexagon, not the circle. Circles leave gaps when packed together, wasting space and requiring additional wax to seal. Not the square. Squares tile without gaps, but enclose less area per unit of perimeter than hexagons. Not the triangle. Same problem. The hexagon sits at the precise mathematical intersection of maximum storage and minimum material. And here is where the mechanism becomes extraordinary. Bees don't calculate this. They don't measure angles. They begin by constructing circular cells, pressing their warm bodies against soft wax, naturally forming rounded shapes. But as multiple bees work simultaneously from different positions, the circular walls press against each other. Surface tension in the warm wax pulls the shared walls into flat planes. The circles transform under physical pressure into hexagons, spontaneously, inevitably. Through the interaction of competing forces and material properties, layers of hexagonal cells sandwiched between solid sheets, providing extraordinary strength-to-weight ratios, impossible to achieve with solid materials. The same structure appears in satellite components, racing car bodywork, architectural facades, and helmet padding systems. Every application exploits the same property the bee colony depended on: maximum structural integrity from minimum material. The geometry that kept a wild colony alive through prehistoric winters now keeps aircraft in the sky and astronauts alive in space. The same math, the same solution, discovered independently by insects and engineers, because the universe only has one correct answer to the problem of efficient space filling. The bee never learned mathematics. It never needed to. It simply operated under survival pressure long enough that the mathematics revealed itself through the physics of the materials involved. Every wall shared between two cells saves wax. Every angle optimized reduces cost. Every hexagon in a perfect hive represents a colony that solved the efficiency problem completely and survived because of it. Nature doesn't find beautiful solutions. It finds necessary ones. And necessary solutions, applied consistently over millions of years of pressure, always turn out to be beautiful. Subscribe to Simple Facts, because the most elegant engineering in the world was never drawn on a blueprint. It was discovered by something that couldn't afford to get it wrong.